So now we're going to add vectors together, and so really what you're doing is constructing a picture. And it's nice because you can see what's going on. It's not so abstract. So we're going to make a picture of what it looks like when you add vectors. And when you add, we're going to take the tip and we're going to add, okay, to the tail. So what does that look like? So if I have vector A, and I'm going to use vector B. We should probably capitalize that and put a little arrow on top. Let's use vector B. And B is going to be longer than A. And it looks like it's going directly horizontal. So when I add that, I'm going to take and add tip to tail. So I'm going to take the tip of A, so that should be vector A, same direction, same distance. And I'm going to add vector B onto this. So vector B was a little bit longer. And what we're going to get is the resultant. So if this was, say, me walking, and somebody came and started pushing me directly horizontal, it would push me off track. I like to dash the line that we call our resultant. This is our resultant. Resultant is the result of the two forces, vector A and vector B, on an object. So it's going to push me and make me go faster, and it's changing my direction. That would be vector B, so that would be my resultant. And we can continue adding A to B and so forth. But what you're going to be trying to do is find your resultant. So here's an example. You have a plane traveling due north at 240 kilometers per hour. So I'm not going to draw this necessarily to scale. But here is my vector. Here's a representation of that vector. That's called due north. So what they're looking at is this is north, south, east, and west. And then I have this wind blowing. So if this is a plane and there's some wind, it's going to blow me off course. And the wind is blowing directly due east. So that means I've just formed this little right angle. And that's going to allow me to use SOHCAHTOA and Pythagorean. So this little black vector is my wind, and it is 10 in magnitude. So the resultant is my plane is going to head a little bit more toward the east and no longer due north. And that's pretty important to be able to find that, because I'll need to correct for that wind blowing. So the resultant, this is the resultant. So the resultant vector, notice the wind made me go faster because it is the hypotenuse of this right triangle. So the resultant would be, we're going to call it the resultant of vector V. So we're going to call this vector, would be equal to the square root of 240 squared plus 10 squared. Okay, so this is just an application of what we were doing before. So change in direction. This would be the angle I would be looking for. I'm going to call it theta. And again, it's still the tangent. So the tangent of theta is equal to side opposite 10 over side adjacent, which is 240 degrees. Sorry, it's not degrees. 240 theta is degrees. So in my calculator, I could find that. I could go second tangent of 10 divided by 240. You know it's going to blow me off course, but it's only going to blow me off course to about 2 degrees. Well, if I'm flying, 2 degrees could be quite a difference. So theta is 2 degrees. So that's the angle. Remember earlier we were measuring the angle off of the x-axis. That would not be how far I was taken off course. So be careful about what you're looking for. You won't have to do really any problems like this. I just wanted to model like what good is what we're finding here. How can I put it into a context? So now I have a plane headed due north at 300 kilometers. It's still encountering a wind, but notice the wind is south of west. So what I like to do is at the end of this, called the tip, where I'm adding my new vector, southwest. Well, I know that this is west, this is south, so when they say that, they just mean exactly that little 45er there. So if the wind is pushing at me, it's more like not quite a headwind, but it's definitely going to slow me down. And I'm going to put this 300 on the other side so it doesn't get in my way. And this dashed line is the resultant. The result is the direction, okay, and how fast my plane would now be traveling. And so this black one here is 10. So if I want to find these measurements, I cannot use right triangle trig. So earlier you'd learned about the law of sines and the law of cosines. And so if I look at this resultant, I'm looking at this dashed line. This is the resultant vector I'm looking for. I need to know this angle. Well, if I expand that, I'm going to zoom in on that angle. I had this going on. My blue vector was coming in. My black vector was coming out. So if I take a look, if this is 45, I believe that this would also be 45. So I now know this theta. So again, I'm looking. I cannot use right triangle trig, but I have two sides. So I'm going to kind of expand this a little bit. So you can see I have two sides, 10, 300. I'm looking for this side, and I know this is 45. So this is x that I'm looking for. So it looks like this would be the law of cosine. I'm going to set it up. It doesn't mean that you have problems like this. I just want to model what would happen. So the vector I'm looking for squared is equal to, so I'm going to take my two sides. So I'm just using my law of cosine. Look it up if you're not sure. It's 10 squared plus 300 squared minus 2 times 10 times 300 times the cosine of 45. So I could plug that in to my calculator. Okay, so 10 squared plus 300 squared, and then minus 2 times 10 times 300 cosine 45, and it looks like that length, ooh, that's huge, but remember, that needs to be square rooted. So the square root of that number, which I'm just going to round, gives me a length of about 291. So my vector is 291 in length. So we want to have that magnitude on the outside. So you could tell it looks visually shorter, and it is. And if I drew it to scale, I could actually find it. So the last thing I want to know is the change in direction. So I'm looking for this little angle right here. So I cannot use the law of, I cannot use SOHCAHTOA or Pythagorean. It's not a right triangle. So if I set this up, it looks like I have enough information. I have the sine of 45, this angle right here. I found this to be 291 is equal to the sine of the angle I'm looking for to its side opposite. So solving this for theta, just so we can kind of see what it would be, it'd be 10 sine, and my calculator is in degrees, I always want to check that, divided by 291, and then I have to inverse sine that value, so it's 0.024. I'm just going to round it a little bit here. It looks like that angle is only about 1.37 degrees, so really not very much, and it wouldn't seem as much because the plane has much more velocity than the wind. It's much faster, but the wind will still affect it. And again, if you're flying 1 degree, can really take you off course if you're flying for any great length of time.